What is a NoSQL database? And what's the difference between that and a relational database? Are all NoSQL databases similar or the same, or are there different types? And if so, what are those types and how are they different from each other? Last but not least, when do we use a NoSQL database and when do we use a relational database? These are all very important questions, and to find out the answers, let's watch together. Hello and welcome. My name is Amr Al-Helu, and today I'm going to be talking about NoSQL databases and how they differ from relational databases. I've already talked about relational databases in a bunch of videos, and I have a playlist about that. I will be linking this playlist in the description and maybe on the screen here as well, so feel free to check this out if you want to learn more about relational databases. But we can also do a quick refresh of that information just to kind of lead into our video today. Relational databases are databases that follow the relational model. What does that mean? It means that data is represented in what we call relations or tables. Each relation represents objects or entities of a particular type, and they have a set of attributes. All the objects of that type have the same set of attributes. Each object or each entity is represented as a tuple or as a row in that table or in that relation, and each of those tuples provides the values for these attributes. So if we look at an example, let's say we have a table or a relation about employees. Each of the employees has an ID, it has a name, and then the joining date where they started their job. So these are the attributes. Each employee is represented as a tuple in that relation. So we can see all the different employees. Each of them has the values for those attributes. Also, usually each relation or each table has something called a primary key, which is one or more attributes that we use to uniquely identify a tuple. Some of the most common relational databases that you may have heard of are Oracle, SQL Server, MySQL, Postgres, and much more. All of them use a query that's called SQL or SQL. This is why also another name for relational databases is SQL databases. This SQL language or SQL language is a language that is used to both read as well as manipulate the data in a relational database system. All of the relational database systems, they use the same SQL language. It has the same syntax everywhere. There might be some minor differences that where each of these systems they add some extra features, but for the most part, it's the same language. So if you have some queries that, let's say, that work in Microsoft SQL Server, most of the time you can easily take those queries and also run them on Postgres or on Oracle and so on. Again, except for some minor differences. Tables or relations, they have to have a definition which includes all the attributes in that table. Each attribute, what is it called, the name of the attribute, the type of the data in the attribute, whether it's like an integer or date or a string and so on, whether this attribute allows null values or not. Also for the relation, what is the primary key of the relation, and other information that is basically part of that definition. This definition usually is referred to as the schema of that table or of that relation. And this schema is usually fixed and predefined. When we say predefined, it means that we have to explicitly define that schema before we start adding data to the table. And as I said, like most or all, technically all of the data in that table must have that same schema. If we want to change the schema at some point, we can, but again, this is something that we have to do explicitly. So we have to explicitly say, hey, like I want to, let's say, add an attribute or remove an attribute or something like that. So this has to be done in an explicit fashion before we start adding any data that follows the changed schema. All right, let's see a quick example in Postgres to illustrate this whole schema thing and how we can modify the schema or create tables and so on. So if I start with creating a table like this, I'm going to create a table called person with two attributes, ID and name. So each attribute I have to specify what is the type. And also in this case, I'm also saying that the ID attribute is the primary key. So this will create the table. If I want to display the contents of that table, I'm going to do select star from this table person. Now the table is empty, but it has been created due to the schema that I provided. Now let's try to insert some data in that table. So I'm going to insert two tuples. One of them has the ID 1 named John, the other has ID 2 and name Alice. So we inserted these two. To make sure that they have been inserted, I'm going to select start from person. Now we can see the two tuples that we have added here. Suppose that I want to add a third attribute, age, for example. I forgot to add that in the beginning. I cannot just go ahead and insert a new tuple that has age into it. I need to modify the schema of the table. So I do that using the alter table command. So in this case, I'm going to say alter table person, add column. The name of the column is going to be age, and the type is integer. So I have to do this before I can insert any data into that column. So I executed this command. Now, if you look at the table, now it has three attributes. We added the age attribute. For the existing rows, we have not entered values for that. So the age attribute for those is empty or null. But now I can add new tuples that may have this value, or I can actually update also that for the existing tuples if I want. So if I want to update this for the existing ones, I could do something like, update person set age equals 20 or something like that. So now if you look at the table, we have updated this tuple, we have updated this attribute to this value. Of course, I can do like a more fine-grained updates. I can do, for example, update set age equals 25, where ID equals 2. So I'm going to just update the row that has ID equals 2. So now this one has been updated to 25. So again, before doing anything with the age, I needed to specify or add that column explicitly first. And now we can add like, a third tuple that has this value already. So I can do something like this, insert into person, now values 3, Emily 30. So we added a new tuple that has all the three attributes, and we can see that here. So just to illustrate the whole thing of like, trying to modify the structure of a table. All right, now let's talk about NoSQL databases. NoSQL databases is pretty much the opposite of what we just said, most of it at least. So first of all, it does not follow the relational model, which is also why sometimes we refer to it as non-relational databases. The data is not structured. I should not say it's not structured. The data is semi-structured, which means that it still may have some structure, but it's not as rigid or as fixed as we have in the relational databases. The schema, however, is very much more flexible. So you don't usually have to define the schema explicitly before inserting the data. The schema kind of like, evolves as you start adding or deleting data in NoSQL databases. Another difference is that it does not have a unified language across all NoSQL database systems, like we have seen SQL. Each NoSQL database has its own language, has its own API that you can use in order to interact with the data in that system. So in that sense, it's different because you usually cannot directly take your queries from one system and use them in another. Let me get back to the first point that I said. It's not relational, right? So the data is not represented as tables and rows and columns and stuff like that. So then how or what does the data look like? That depends on what kind of NoSQL database we're talking about. On a high level, there are more or less 4 types of NoSQL databases, and we're going to talk about each of them and see what the data looks like in those. The first type is graph databases. Graph databases, as kind of like, is evident by the name, they represent the data as a graph. If we know graphs, we know that graphs usually have nodes and they have edges. Nodes usually represent the entities, and then edges represent the relationships between those entities. Each node will have some attributes in it. Also, in many of the cases, the edges will also have some attributes in them as well. What's an example of a graph database? Like, think about something as a like social media, right? Something like Facebook or Instagram and so on. If you think, all users are entities. You have things like posts, comments, groups, events, media, like pictures or videos, reels, all of these things. Each one of these things is an entity. So you can think of each one of these things as a node in the graph. For a user node, for example, it will have all the user information in that node, like name, join date, age, country, whatever, like, all the user information will be in that node. Something like a post, it would have, the post text, the date of the post, if it has any images or links or something like that. Those actually might be their own nodes and they will be connected to the post. And then the post will be also connected to the user that posted this. So this is where the edge comes in. If you have comments, each comment will have, the comment text. It will be linked to the, let's say, the post where this comment is commenting on, and it will also be linked to the user that posted the comment. So this is how, the different parts of the graph will be connected. Any graph database needs to provide some way to query that data. So usually you have the usual operations that you want to do. You want to filter by something, you want to project certain attributes, you want to do some aggregations, grouping, stuff like that. But additionally, in graph databases, you also need to provide something that will allow you to traverse the graph. So saying something like, hey, start from user with ID 123, go to all the other users that are connected to this one, and then filter them by region, and give me the ones with the top number of comments or something like that. So you start from one type of node, and then you jump the graph to a different kind of node, and then apply some filters and so on. So this is the kind of thing that you should be able to do in a graph database. Some examples of graph database systems, you have Tiger Graph, and there's also Cosmos DB are maybe two of the most popular ones. The second type of NoSQL databases is key value stores or key value databases. You can think of that as just something that stores pairs of keys and values. The key is usually just some kind of object or value used at the key. And then the value part of that pair could be either some atomic values like integers, strings, dates, and so on. But it can also be something more complex, like it could be a whole object or an array, or a media object like a video or an image or something like that. So the value could be pretty much anything. You can think of that as a hash table, basically, where the key is the hash key and then something is stored in the value part of the hash table. We know that hash tables are very fast to access, single elements. If you want to access a single element, like you have a point query, you can get it in big O of 1, it's basically constant time. So for that reason, key value stores are very useful for systems that you want to use for point queries. Things where you want to look for something and get it very fast, or you want to update something and do it very fast, one item at a time. So an example for that would be, let's say you have a web application, for example, and you're storing some session information with every user, right? So you have all these requests coming to you from different users, and you want to be able to, for each request, go and grab the session information for that user and present the data to them in a way that, let's say, satisfies some preferences and something like that. So if you maintain a key value database where the key is the user ID, you can easily get that information very fast, and your application would be super fast. Another example to use something like this would be in caching. If you want to implement a cache for whatever reason, you could use a key value store as your cache layer, where you have a way of computing a hash key for the cache, and then you can look up very quickly to see if something is already existing in the cache or not. So there are different applications where you can use something like that. It's very fast for point queries. One of the popular key value stores is RocksDB. The third type of NoSQL databases is wide column stores. So think of columns as we've seen them in relational databases. So a column is basically one attribute, right? In relational databases, you store all the tuples together with all the data of each tuple. In wide column stores, we focus on the columns, and we could store either one or multiple columns together if we always want to access all these columns together. This is usually very useful for analytical queries that want to do some operations on a full column or multiple columns. For example, if you have sales information and you want to get the sum of sales in a particular year or in a particular quarter, or you get you want to do some statistical analysis on all the sales values. So if you have just the column for sales values, you can do a lot of operations on that very quickly. You might combine multiple columns together and so on. So this is something where you could use something like that. Some examples of these systems are Cassandra, and also there is Bigtable from Google. The fourth type is what we refer to as document databases. Document databases do not store documents like in the sense of PDF documents or Microsoft Word or Google Docs or something like that. We're talking about some kind of semi-structured document. Think something like XML document, for example, or more popular is JSON documents. JSON documents, we can show an example here, is a semi-structured type of document that has fields, and each field has a value. The value could be an atomic type, or it also supports things like arrays, nested documents, and so on. So each object is referred to as a document. So yeah, you could have multiple levels of nesting and so on. To kind of like contrast that with relational databases, so in relational databases, each object is a tuple, right? In a table or in a relation that has all the tuples for that type of entity. In a document database, each object is a document that has all these fields, and then a group of such documents is called a collection. So the collection is basically an analogy to the table in the relational world. So you would have let's say an employee collection or a car collection and so on. And each employee would be a document with all the employee information in that document. Some of the popular document databases are MongoDB and Couchbase, for example. These are some of the most popular ones. Okay, so let's see a quick example on MongoDB to see what the documents look like and how it can have nested objects and nested fields and so on. So I already created a collection called orders, which you can think of it like a table in a relational database, but here we call it collection. So this collection has data about different shopping orders, for example. So to list all the contents, I can do db, which is the database name .orders, which is the collection name .find, and I specify no conditions here. So this is simply going to list all the contents of the orders collection. So in this case, the orders collection has 3 documents. This is a document, and each document is representing a single order in our case. So you can see it has some top-level fields like a customer and a location. Each document by default gets an ID, underscore ID. This is kind of like a system field that gets added by default to each document. And then we also see there are some nested fields. We have an array called items that could be one or more elements that represent the items in this order. So each item has description, quantity, and price. So okay, so now we displayed all the collections, all the documents in our collection. How do we filter this? How do we display just a subset of these? So let's say, for example, that I want to get all the documents that have location equals to London. You can see there's 2 of them here, and then there's one which has the location equals to New York. So what I can do is, in the find command, I'm going to specify a condition, which is location is equal to London. So in this case, we only showed these 2 documents that have this location. I can also try to limit the amount of information that's being shown. Here we're showing all the contents of the document. But what if we only want to show, let's say, the customer and the location? We don't want to show the items. So to do that, I have to add another part in that find command, which is basically like the projection or the list of output fields. So then it would look like this. So we still have the condition, which is location equals to London, but now I added another kind of part here of the command, which is which fields to actually return. In this case, I'm returning the customer and the location fields. 1 here means basically true, or these should be included in the output. So if I run this is the result that we get. So we get still the same documents, but we're getting only the fields that we specified. Note that the ID field is already shown by default. Even though we did not specify it here, it's shown by default. If we want to actually not return the ID, we can add it here with a 0. value. So it means basically to hide that field. So then this is what we get in this case. So now we have seen how to make or how to query that collection with a condition on a top level field, which is the location in this case. How do we do a condition on a nested field? Let's say I want all the orders that have a notebook item in them. So if we look here, so here, for example, this one has a list of items. One of them has a description equals notebook. So to address this items dot description, this is how we are going to refer to that nested field. So the query will look like this. So db.orders defined. Now I'm looking for the items dot description equals to notebook. So this will return all the documents that have a notebook within the items array. So these two have a notebook here. So we return those two documents. So this is how we do a filter on one of the nested items within a document. Okay, now that we know what types are there of NoSQL databases, let's talk about some of the differences between relational and NoSQL databases. One of the main differences, which we have already kind of like hinted at, is the way the data is organized or the way the data is seen. I'm going to be talking mostly about document databases on the NoSQL side, but we might also talk about some things that touch on other types of NoSQL databases. So in terms of data organization, let's look at an example. Suppose this is an example of a shopping order, very simple. It has some information about the order itself in the header, which are things like the order number, the customer, the date, the location of the store where this order happens. And then you have some details about the items that were bought in that order, right? So how would this be stored in a relational database? In a relational database, typically this would be stored in two different tables. You would have one table for the order header and then another table for the details or the line items. And the common data between them would be the order ID. This format is something that we call normalized data. It's normalized because the data is kind of like split into multiple parts to avoid duplication or repetition. If we were not to split this, basically if we want to store this all in one table, we would be duplicating the order information, like with each item we would repeat the same customer and the same store ID and the same location and all that. So this would be like a denormalized data storage format. For the normalized format, which is the most popular, we store it in this way. So as we've said, the data is linked through, let's say, the order ID. So if you want to get all the information for order 156, you need to get the header information from the orders table, and then you need to get the details from the line items. And we know how to combine them. In relational world, we use joins. So we can join on the order ID to combine all that information together. And we can see that in this demo. Okay, let's see how this looks like on Postgres. For example, I have the two tables here, orders and line items. I've already defined them and added some data. So let's take a look. This is the orders table. Each order has order ID, customer, order date, and location. And we have 3 orders here. And then if we look at the line items table as well, this is the data that we have. So each line item has the order ID, so it refers to the order ID from the orders table, and then it has a line number, item, quantity, and price. So each order, like for example 156, has its details in here with the same OID, and so on for the other orders. So if I want to combine these two tables to see all the information together, all I have to do is to do a join on the OID field. So I can have a query like this that says, select from orders, join line items on this condition. So orders.oid equal line items.oid. So this will display all the information from both tables joined on the OID column. If I want to see just the information for one particular order, for example, order number 156, then all I need to do is add another condition after that. So query would look like this. I added where orders.oid equal 156. So this will display only the information for that particular order. Now, let's say I remember that I actually forgot to add a third line item. maybe this order should have 3 line items, not 2. And the third one was, let's say, a book. So I can easily update the line item table by doing another insert here. So I can insert into this line items table, specifying the order ID number, line number, and then the item information. And then if I select again, you can see all the information that we just added is already there, and it's also joined with the orders table as usual. I can do the reverse. I can delete that if I decided that I maybe inserted it incorrectly or it shouldn't be there. So I can do something like this, delete from line items where, specifying the order ID and the line number. And this will delete that row. Again, to verify, we look at the table and it's not there anymore. So we can see it's very easy to delete or update or insert something in the details, regardless of what's the data in the header looks like and without even having to touch that. As we have seen as well, it's very easy to add, update, or delete, let's say, the information in the line items, right? Because it's separate from the orders table. So if you want to add something or if you want to delete something, you can do that easily without touching the orders table at all. So this is, again, one of the benefits of this normalized form. Another benefit of this organization is that the size of each row is not that big. If we were to store it denormalized and we store everything together, then the size can be pretty big. It might be very difficult to manage. But because we have it in this form, the size of each row is manageable. The downside, of course, is we have to do that join thing, right? Before we are able to combine the data and be able to process the data together, we have to do this join. Okay, what would this look like in a document database like MongoDB, for example? This would most likely look like this. So we have a document representing the order. All the related data is together. So this is the document representing this order. It has the header information. It also has an array for the items, where each item has, the description, the quantity, the price, and so on. Having this all data together means that we can easily retrieve this data and we do not need to do a join because the data is already there. The downside is that it can be difficult to do any, let's say, updates or deletes or inserts on the line items because, again, the unit here is the document, so we need to overwrite this document. There are ways that you can do this kind of like, update, but it's not very intuitive and it's not very easy. The other downside is that the documents can get too large. Like if we keep adding, for example, line items, or if one order has too many line items, then this document will be huge. And let's say we want to somehow deal with this and bring this into memory, then we might have to deal with, does it all fit in memory or not, and so on. So there are considerations there regarding document sizes and so on. Another difference between relational and NoSQL databases has to do with scaling. First of all, let's talk about what scaling is. So scaling means that as your data grows, as your use cases and queries grow, you need to upgrade your system to be able to deal with that. Generally speaking, there are two kinds of scaling. There is vertical scaling and horizontal scaling. Vertical scaling means that you increase the capabilities or increase the specs of your server or your machine to be able to handle, let's say, more data, more queries. You can do this by, let's say, adding more memory, upgrading your CPU, adding more disks, all that to the same machine or the same server that you have. This obviously has a limit. Like, at some point you're going to hit a limit and you will not be able to upgrade more than that. Horizontal scaling does not increase the specs of a machine. It increases the number of machines or the number of nodes or the number of servers that you are dealing with. This could be real machines or virtual machines. So basically you rely on adding more rather than upgrading one server. And you rely on being able to do operations in parallel so that each machine can deal with, part of the data or part of the queries. So, okay, so how does this happen in relational databases and in NoSQL databases? If we look at relational databases, traditionally, it used to depend on vertical scaling. So you have a database on a single server, you want to add more data or you want to be able to support more queries, you increase the specs of that server. You would, upgrade the memory, you upgrade the CPU, you would add more storage and so on and so forth as much as you want until obviously you hit that limit. So that's how it used to be traditionally. Now, with the addition of distributed database systems, this also started to incorporate horizontal scaling, which in databases is usually known as or uses something called sharding or partitioning. There are two kinds of that as well. So if you look at each table, you can partition it in two ways. You can partition it horizontally or vertically. These are all part of the part of the horizontal scaling. So to shard a table vertically, it means that you split the attributes. So some attributes will be in shard 1, some attributes will be in shard 2. If your query deals only with the attributes on shard 1, then it only needs to be handled there. Same thing with shard 2. If you need both, then both can work, and then you need to join the data somehow. Horizontal sharding splits the data by tuples. So you can say, let's say, from the ID of range from 1 to 100 is going to be on the first partition. From 101 to 200 is going to be in the second partition, and so on. And again, you can have your queries run in parallel on those partitions, and then you combine the data at the end. So these are two ways to do partitioning in distributed databases. For NoSQL databases, they have been already designed to handle huge amounts of data. They have been designed with horizontal scaling in mind. So usually it's already by definition, they are running on multiple instances, virtual or physical. Whenever you want to expand, you just add more servers. This whole scaling thing is usually invisible to the user. The user doesn't know what's happening behind the scenes. The storing of the data on multiple servers and then being able to combine this data usually happens all behind the scenes. The user has no idea this is happening. Because of how data is represented, you typically don't need that many joins in NoSQL databases. So this basically increases the opportunity to do operations in parallel among nodes. So each node can do separate part of the computation by itself, and the need for joins is very, very, very minimal. So yeah, this increases the parallelism. The next part we're going to talk about is transaction support in relational databases and NoSQL databases. First of all, what is transaction? A transaction is, you can define it as a group of operations that need to happen together. Let's see an example to try to understand the concept. Suppose that we're doing like a money transfer from one account to another account. This could be like a bank transfer, or it could be as simple as like you're sending, money to a friend using Venmo or PayPal or something like that. These are two operations that are happening at the same time. You need to subtract an amount of money from your account, and you want to add the same amount of money to a different account. Those are two operations. And both of them must either happen or not happen. You cannot have the case where one operation succeeds and the other fails. If, let's say, the first operation succeeds and the second fails, it means that you subtracted money from one account, but the money didn't make it to the other account. So overall, the money is missing. If the opposite happens, then the money did not get subtracted, but it got added. So money just got added from thin air. So this does not make sense. So treat those two operations as a unit that needs to either happen together, which we call commit, or they need to, if let's say some error happened or something, then we need to cancel both of them together, which is called rollback. When we talk about transactions, we talk about something called the ACID properties. ACID properties is an acronym for 4 different words: atomicity, consistency, isolation, and durability. Atomicity means what we were just saying, basically, that the whole transaction, all the operations in the transaction are treated as an atomic thing. It should either all succeed or should all fail. It's an all or nothing. Consistency means that the data needs to be in a consistent state after the transaction is done. It needs to be correct. It cannot be in a state that is incorrect or corrupted. For example, the money that we said, the consistent state means that, let's say, the total amount of money that were in both accounts before the operation was $1,000. After the operation, it needs to be in that same consistent state where the total is still $1,000. So transactions need to guarantee that. Isolation means that if we have multiple transactions happening at the same time, then we need to treat them as if each of them is happening in isolation. There should not be any interaction between them. So if you're doing, let's say, multiple transfers on the same account, we should be able to treat them as if they're happening one after the other, to avoid things like dirty reads and so on. Durability means that the data after a transaction is committed should be durable and should be persisted, and if something happens after that, that change is already saved. So if, let's say, we did that money transfer, we committed the transaction, so now the new state, let's say something happens after that crash or whatever, that new state is saved and nothing should change that. So these properties, whether or not they are supported, is what tells us whether a system supports transactions or not. So if we look at relational databases, usually most, if not all of relational databases, they support these asset properties and support transactions. Some of them may not, but for the majority of relational databases, they do support and enforce these properties. If we look at NoSQL databases, that's not always the case. Many of them do not support transactions. They do not support asset properties. They may support a subset of these properties, but not all of them. However, a few NoSQL databases, including MongoDB, actually it supports transactions and supports the asset properties. All right, so the next thing to look at would be the use cases. When is it more appropriate to use relational databases versus NoSQL databases? Relational databases are usually used when we are looking at a system that needs to support transactions. Like if we're looking at most financial systems, whether it's something like a banking system or an e-commerce system, anything that has to do with money usually needs to support transactions, so most of them end up using relational databases. Systems that have complex queries. Usually using SQL, you can express queries that are very complex with lots of joins, lots of operations like aggregations, subqueries, and so on and so forth. So complex queries are usually easy to express in relational databases. The main reason why you choose a relational database is usually because your data is structured. If your data already kind of lends itself to a relational model, like the data has very strict schema, all the entities of any type follow the same schema, they have the same set of attributes, then this looks like something that you would use a relational database for. When is NoSQL database used? When it's the opposite of that. If you don't need transactions, if you're looking for something that is highly scalable with support for a lot of data, if you're looking for something that has a flexible schema, maybe it still has some structure, but maybe you don't want something that's super rigid and you want to be able to kind of modify your schema on the go, especially let's say if you're starting a new application or something and you're not really settled yet on the final form of your schema, then maybe a NoSQL database would be most appropriate, at least in that stage. So yeah, those are some of the different use cases where you would choose one over the other. Okay, so after going over these differences, let's just recap everything that we talked about, compare SQL databases or relational databases to non-relational or NoSQL databases. So again, we talked about the structure. Relational databases have structured data, follows the relational model. Data is represented as relations that consist of tuples and that have the same attributes. The schema is usually predefined and it's fixed. You can change it, but you have to change it explicitly. In NoSQL databases, the data is not relational. It can be graph data, it can be key value tuples, it can be documents, like JSON documents and so on. You usually have a flexible schema. You don't need to define the schema beforehand. It kind of it can evolve with you as you go. Relational databases, they use SQL to query the data, whereas non-relational databases, they use multiple different languages depending on each system. Relational databases, they traditionally use vertical scaling, but they also use partitioning, especially in distributed databases, whereas NoSQL databases, they are heavily parallelizable, heavily reliant on horizontal scaling. Relational databases often support and enforce ACID properties and have transaction support, whereas this is not guaranteed in all NoSQL databases. Some of them do, but not all of them. And then in terms of use cases, relational databases are often used for cases that have structured data and require, for example, transactional support, whereas NoSQL databases are used when you have not so structured data, when you need a flexible schema, when you don't need transactional support as much. So yeah, these are some of the differences between the two types of databases. Hopefully that kind of like, cleared up some of the misconceptions or some of the questions that some of you may have had. I'm planning to make more videos to talk about NoSQL databases in more details, just like I have a series of videos on relational databases. So stay tuned for that. Subscribe to the channel to get all the updates on that. If you have any questions or if you want me to talk about certain topics, please leave a comment. And as usual, like and share the videos if you thought it was useful. With that, thank you so much for tuning in, and see you in the next video.